guessing blank on this.
Yeah. Okay.
But that helps word said a capacitor was a battery.
No, I think the basic definition that we gave is actually a very good definition. That capacitor, the name itself implies that it has a capacity. So it has a capacity of storing charges. Okay. And something has a higher capacitance means that something is able to store more charges. Okay. So before I go on further explanations of electrical capacitance, let me give an example from a mechanical object. Like when we say a container has a big capacity, what does it really mean? Let's say that we are talking about a beaker. So the beaker can contain liquid inside it, and the bigger the beaker, the bigger the capacity, right? That's everyone understands, right? Shouldn't be any questions on it. And if you pour more liquid on this beaker at one point of time, the liquid will spill out. So this means that you are going over the capacity of the beaker. In a similar way, if you put some charges on a material, let's say that this is a ball made of metals, and you are trying to put some charges on it. How you can put charges on it? What is the easiest way to put charges on it? What is your thought? Go ahead.
I just said charge it.
And how do you charge it?
Some kind of applied electric field.
Piece of tape. Piece of tape.
Yeah, good, very good. So the idea here is that we have to rub it, right? We have to create a friction, and then it will create charges. And the other possible way is that you connect with a battery. That's exactly what she's saying. And maybe if you have another object, if you have another bigger object, which also contains some charges, if you connect these two guys with a conductor, they will also transfer charges. Okay? So let's look at this scenario. Let's say that this guy was initially neutral, so no charge was there. And on the other hand, I have something which is very big, and it has a lot of charges. If I connect these two guys with a conductor, then this guy, this big guy, is going to transfer the charges to the charge neutral object. So it will also get some charges, right? So there will be charge transfer process. Will the charge transfer process keep going on forever? Or will it come to a stop at some point? Equilibrium. Okay. Equilibrium of what? Equilibrium of charges?
Yeah.
Charge.
When both of them have same charges?
Charge density between the two.
Charge density. Yeah. Charge density. It's somewhat better answer.
Okay.
But there is an even more better answer. What is that? You know it. When some things stop flowing charges, there is no more charge. Just think about Coulomb's law. What does it say?
Voltage.
Voltage. And why do you say voltage? It's because Coulomb's law says the amount of current is proportional to the voltage. V is proportional to I, right? So as long as there is a voltage difference, we must have a charge transfer between them. So when there is no more charge transfer, we can say that the voltage V1 and voltage V2 will become equal when they will reach an equilibrium. Alright? So charge transfer keeps going on until they have the same voltage. Alright? Okay. So tell you this thing. Let's say that we are trying to store charge inside a sphere. And how do we store charge? We bring some other charges from the space to the vicinity of the object. So let us say that this guy, it already have acquired some charges. If I bring another positive charge here, I should feel a force, right? Should I feel a repulsive force or attractive force? If I bring more positive charges, repulsive forces, right? So this means when you try to populate more charges, you should feel a repulsion force. So it discourages you from getting more charges, right? And at one point of time, the repulsion would increase so high that you would be very heavily penalized to add one more charges on that object. So just like the way you cannot put arbitrary amount of liquid on a beaker, you cannot put arbitrary amount of charges on an object. Because each time you add a charge, you are going to feel more forces next time you add another charge. Do you follow? So, when we say about capacitive, when we talk about the capacitance, electrical capacitance, and we say that one object has a higher capacitance, it means that this guy, which has a higher capacitance, it has less repulsion forces when you try to add more charges on it. So, probably you know that a capacitance can be made. The simplest way of making a capacitor is taking two plates, metal conductors, separated by some dielectric. So these are two conductors, and I hope that you know that these two conductors, if you count them, if you bring them close to each other, they will form a capacitance. You know it, right? Okay. So when we say that this capacitance is bigger than some other capacitance, basically we mean that the bigger capacitance will have less resistance to bring another charge on top of it. So if I take two metal plates, so one is small and one is large. So let's say this one is small, parallel plate, and this guy has a large parallel plate. So we know that the capacitance is typically defined as EA over D, where D is the distance between two metal plates and A is the area of the capacitor, of the capacitance plate. You know about this equation, right? Previously, okay. So I'm not going to explain it, but let's look at the implication. It says that if a capacitor has larger area, if a plate has larger area, it will have higher capacitance. Now, I said previously that higher capacitance means it has less resistance towards an incoming charges. And while this guy applies a less resistance towards an incoming charge compared to the smaller guy, it's because if you keep pumping in more charges, they will have more spaces to spread out. So this is why these guys, they will keep repelling the other incoming charges compared to this other guy, where you have more charges to spread out in both top conductor and the bottom conductor. Am I explaining this idea? That why a bigger plate has a bigger capacitance? A bigger plate has a bigger capacitance because now we have more spaces to spread out the charges so that the charge density reduces. If charge density reduces, then you will have less Coulombic repulsions to an incoming charge. That's why you can pour more charge on it, okay? So that's why the name capacitance comes from, that it can house more charges, all right? So in order to increase the capacitance value, what we are going to do, just look at those two metal plates and tell me what are some possible ways to increase capacitance.
Decrease distance or increase area.
Very good. So one idea that you increase the area. If you increase the area, then of course your charge will have more space to spread out. That means it will have less repulsion forces to an incoming charge. So capacitance increases. Okay. These other guy, distance and epsilon, probably it takes little more effort to understand it. Why decreasing the distance would increase capacitance. I mean, of course, if you look at the equation, it's clear that decrease of distance would increase capacitance. But I'm talking about a conceptual viewpoint. Why decreasing distance between two metal plates will reduce the repulsion of to an incoming charges? Any thought?
Is it because when you increase them, decrease the distance, there's gonna be more attractive force from the other plate?
Very good. Yep, exactly. Yes, go ahead.
Is it also fair to assume that like there's not a true vacuum in between them, there's like air, which leaves an insulator, so the less insulation between them, higher conductivity and higher capacitance, is that?
No, don't fix the conductivity. Conductivity is a different idea.
Okay, so this is, yeah, so it's not helpful to think about it in terms of like the insulative barrier in between them, right?
Say it one more time, maybe.
Yeah, so if the space between them is, if we're assuming it to be a true vacuum, then there's no insulation, but there's,
No, vacuum is actually a very good insulator. Vacuum is the best insulator.
right. So if there's less insulation between them, does that imply a better capacitance? Or is this an unrelated?
No, I think that's a good idea, actually. Why? Because let's look at this. If I take two metal plates, and let's say this top metal guy has positive charges, and the bottom metal guy, it will have equal amount of negative charges. Okay? Now, if I bring them closer to each other, what is the most extreme case? In the most extreme case is these two metal plates, they will just touch each other, right? So if they touch each other, what will be their total net charges? 0. So it will apply 0 repulsion to an incoming charge, right? Now this is the most extreme case. Think about the next step. You do not make it exactly contact to each other, but keep some separations. If you keep some separations, then yeah, maybe these guys, this entire guy, can be thought about some charge neutral object to an incoming object. But if you keep increasing the separation between them, let's say you take them further apart, can you consider these guys any more charge neutral? You cannot. So if you bring them very close to each other, an incoming charge which is coming from far surface and trying to get close to these guys, they will not feel any forces because these guys are very close to each other. But if you try keeping them take away further apart from each other, then these guys will start to feel a force from this guy. Do you see the concept here? So the closer the plates are, the more they react like a charge neutral object. If they behave like a charge neutral object, then they will apply less repulsion to an incoming charge. And that's why you can put more charges on it. But if you take them further away, then they cannot be considered as a charge neutral object, and that's why they will apply repulsion forces to an incoming charges. Is it getting too complex?
A little bit.
A little bit? Maybe I'm not wording it in the proper way, but I hope that if you think about it in your idle time, in your safe time, I think you will get the idea. That capacitance can be thought of as a measure of how much charge you are going to put inside an object. So when you put charges inside an object, you will start to feel repulsion forces because of Coulomb's repulsion force, Coulomb's force. So something that has a higher capacitance means something that can apply less Coulomb repulsion force. Okay, so there are two ways to make the Coulomb repulsion less. One, you make the plate bigger so that these charges will have more space to spread out so that charge density reduces. If charge density reduces, it will have less Coulomb repulsions to an incoming charge. That's one way. The other possible way is that you take two metal plates, but you bring them very close to each other so that together they will act as a charge neutral object. If they are charge neutral object, then they will provide less repulsion force to an incoming charge. That means you can put more charges on it without having any significant resistance. So these are the two ways by which we can actually make capacitance very large. And there is another knob which is called epsilon, which is the permittivity. So to know permittivity, we have to look into another property of material. And let us try to understand that how permittivity could help us increase the capacitance. So do you guys remember the experiment that we did with Winshaw's machine, where we have two metal balls and we created charges. We created two opposite charges, plus Q and minus Q, on those Winshaw's machine. And we experimented while we kept some dielectrics in between them. So let's say that we attach some papers on those two metal balls, and we apply some charges on those two metal balls. Do you remember that what happens to those papers? They touch each other. So that means there is some kind of force going through between those two paper pieces. And why there are force? It's because despite the paper itself is dielectric, but when you touch these papers with a charged object, all the atoms, all the molecules of the papers, they get partial charge. So one part of it will get partially negative and the other part of it will get partially positive. Something like this. So the molecules will get a little bit elongated. A part of the molecule which is closer to this charge will become partially negative, and the other part of the molecule will become partially positive. And thus they will create a long chain of molecules where one side of it is partially negative, one side of it is partially positive. And same thing will go to the other guy. This time it will have partially positive charge at one hand and partially negative charge at the other hand. And that's why they will start to attract each other, because they have different kind of charges. So let us now look at the other scenario where we have two parallel plates. So these are metals, let me write it as copper. And inside the copper, let us say we have air. Now the air molecule, if you place some charges on the top and bottom, so positive Q charge at the top and negative Q charge at the bottom, then this guy will start to distort the molecule of the air a little bit. In fact, the molecules of the air would be partially negative at the top and partially positive at the bottom. So we'll have many molecules. Each of the molecules will be partially negative, partially positive at the bottom. Okay, are you guys following? So why I drew it in this way? Take a special note on the sign of the charges. I drew the negative sign whenever the molecules is closer to the positive plate. I drew positive signs whenever the molecules are closer to the negative copper plates. Does it make sense? That why I drew it like this way? Okay. So now let's consider this thing. If this guy is slightly negative, they are going to cancel out the impact of positive charges from the copper plates. If these molecules are slightly positive, they are going to cancel out or slightly compensate the impact of the negative charges on those bottom copper plate. Do you follow? So if they are going to compensate a little bit both the positive charges on the top plate and the negative charge on the bottom plate, they are going to reduce their overall repulsions to an incoming charge. You see? So this is why if you take a material which can be more polarized, which can be more elongated, then the corresponding capacitance would go up, because capacitance is all about how much repulsions do you see to an incoming charge. So instead of air, if you put some better material, for instance, if you put silicon, silicon has more tendency to have polarized material. So if you take silicon material in between top and bottom copper plates, the atoms of the silicon will become more polarized. So it will get more negative charge and more positive charge on both sides. And that's why they can annihilate, they can compensate more the top copper plates charge and the bottom copper plates charge. So that the incoming charges will see less resistance when it tries to get close to these copper plates. Am I making things very complex?
Okay, so just to clarify, you said
Mhm.
the capacitance for the silicon between will be higher than the air?
No, not the capacitance. A material does not have a capacitance. An object has a capacitance. When I say silicon and compare it with air, I say that silicon molecules are more easier to elongate. Okay? If a molecule is easier to elongate, it will create more partial positive charge and more partial negative charge, and that's why they will be able to compensate the copper plate's capacitance. So this is why when you take silicon, the copper plates will have less net positive charge and less net negative charge, so that it can reduce the repulsions on an incoming charges. So in case of air, let me just draw a cartoon. Let's say this is the air molecule. Okay? This is the air molecule. This is the silicon molecule. Let us say. Just cartoon. Now I put both silicon molecule and air molecule in between two copper plates. Let's say this is positive charge, this is negative charge. Same thing here. I put silicon molecule on a positive copper plate and a negative copper plate. Because they have two positive and negative metal plates, there will be some electric fields, right? There will be some electric fields. And also there will be some electric fields here. An air molecule remains almost passive, neutral to an applied electric field. That's why when you look at the distortion of the air molecule, the distortion is very minimal. So maybe an air molecule will have a very little distortions. Very little distortions. That means it will have maybe slightly negative charge and slightly positive charge on its top and bottom. On the other hand, if you take silicon, this guy will strongly respond to an applied electric field. So it will have very large negative charge and very large positive charge on top and bottom. So this is exactly what I mean by when I say that you take a silicon and you increase their capacitance. Do you see this point here?
So is the permittivity the tendency for that object to kind of become partially charged like that?
So when we say that a material has a higher permittivity, it means that this material is more amenable to distort their molecule. Okay? If I can elongate the molecule easier, then I'll be able to compensate for the positive charge and the negative charge at the top and bottom copper plates. And that's why they will apply less repulsion to an incoming charge.
So because the silicon has a higher permittivity than air,
So when we say higher permittivity, it just means that the molecules is easier to distort.
and that's why capacitive
Mhm.
increases, it can replace the free space between it with something like silicon.
Exactly. Exactly. Okay. Is there any questions on this? You understand the core concept, that why I can tune area to increase the capacitance. Again, I can increase the capacitance by increasing the area, because if the area is high, then these charges will have more space to spread out. If the charges spread out more, then they will apply less repulsion force to an incoming charge. I can reduce the distance between two copper plates, because if I reduce the distance, that means that they are going to annihilate their impact on each other on an incoming forces, on an incoming charges. I can also tune the permittivity of the material that is within those copper plates. If I take a silicon which has a high permittivity, they are going to be distorted more, and by having more distortion, they will partially compensate for the positive charge and positive negative charge. And that's why their repulsion on the incoming charge will be less compared to another object which has air molecule in between those copper plates. Do you see this? Okay. So I think we discussed a lot today. Maybe next time on Monday, right? On Monday we'll show some experiment which will help us to better understand that what is capacitance and how capacitance impact our electrical devices.
So Monday,
Tuesday.
it would be Thursday.
Oh,
Oh,
Thursday.
Today's Thursday.
Oh,
Today's
right.
Thursday, but we have break Monday, Tuesday.
We'll see you on Wednesday.
Oh,
We have a quiz on Monday?
Hang on a second. So
no school Monday, Tuesday.
no, hang on a second. Let me understand. So I know that Monday is a holiday, right?
Mhm.
So we have also closure on Thursday.
Monday,
It's
Tuesday.
Tuesday,
Yeah.
fall break.
Okay.
Student recess.
I see.
I guess
So
you're
that-
not so lucky.
So our next meeting will be on Wednesday.
Yes.
Okay. All right. So on Wednesday, as usual, we'll have a short class, and we'll have a short exam also based on whatever we discussed here. So just the syllabus will be this.
Just this.
Just this. Yes. Just capacitance. The idea of capacitance. Okay. All right. And let me quickly tell something in terms of the exam. We have just 5 more minutes left, so I'll be quick, I promise. So in the exam, I said that you are going to face both questions from theory and questions from math. So for the questions that I typically ask from math angle, if you look carefully, let me see, do I have time to just flash my screen? Give me just 1 second, guys. So sometimes I ask questions which requires a little bit of mathematical manipulations. For instance, yesterday we tried to solve this kind of problem where we have a copper inner core and a dielectric outer core, and we tried to find out the corresponding resistance and power, etc., for these things. So I know that many of you were able to solve these questions. Congratulations. Some of you probably tried, but probably couldn't get to the final answer. So let me tell you how exactly I'm gonna solve this question if I were asked the same thing. Before you solve this question, I would suggest that at least for my exam, look at the corresponding options first. Do not try to immediately jump into the problem. Look at the answer. So what is the answer here? For instance, multiple choice, it says what is the resistance of the outer surface? 1.9, 50, 0.005 and 100. Do you see that they are widely separated from each other? There is no match even, right? So you don't need to get to the actual decimal point. You can just guess. If your guess is good enough, probably you can get to the right answer even without doing any calculations. So let me tell you this. We have two different layers. One is the copper layer and one is the dielectric layer. Which layer is easy to calculate for resistance? Copper layer, because it's just a solid layer, right? And for this layer, the copper layer, you know that the resistance is equal to the length divided by area divided by their conductivity, right? Okay. So what is the difference between the copper layer and the dielectric layer? Their length is same, right? They are all 5 meters. The only difference is probably their area and their sigma, right? Okay. How about the area? I know the area is not same, but how different are they? Let us try to draw it here. I'll draw it here, okay? So we have a copper core and we have a dielectric layer on top. This is the copper and this is dielectric. And the question says the copper core has a cross section of 1 meter square. So that means what? This guy is probably 1 meter. Is it very wrong if I say that this guy is probably 1 meter? It's not very wrong. Of course, I know that you know you're smart enough to find out what is the exact value. It's pi r square, and pi r square is 1 meter square. And from here, you can get the exact value of resistance. I'm not trying to get to the exact value because the answer, which is they're very wide apart. So even if you get to the ballpark, you're fine. So I would say this copper is actually 1 meter by 1 meter in size. Isn't it easy for us? So I can just say that maybe, let's just ignore this guy. Let's say that this is just a square. It's 1 meter by 1 meter in size. What am I losing? I'm not losing too much because in reality, these coppers are not a square, but they are a sphere. So I'm probably losing something in the corner, but not much. So it's actually okay if I say that this is 1 meter in size. Okay. Look at the diameter of the dielectric layer. It says dielectric layer thickness is what? 0.5. Okay. So this is actually 0.5. This guy is 0.5 meter. So maybe I can redraw this other guy. I say that this is the other surface. Just make it easy. So this is 1 meter. This is 0.5 meter on all four sides. Now tell me, which one is bigger in terms of area? Is the copper has a bigger area or the dielectric have a bigger area? And when I say bigger, we don't need to get to the very details. Just tell me approximately that do they have very different cross-section area or very similar cross-section area? When you say cross-section area, you actually try to see that how many these cubes you are going to fit on those sides. Can I fit 1 cube Can I fit 10 cube?
5.
Can I fit 10 cube here? No. Can I fit 0.01 cube? No. So that means this area and this area are not very different. Like, they are not 10 times different for sure. Are they? They are not. So it's sure that the area that you are trying to find out is not actually very different from the copper itself. So the only big difference, it comes from the sigma. Because copper has a sigma of 10 to the power 7. The dielectric has a sigma of what? Just 1 Siemens per meter. Right? So sigma is the biggest factor here. Not the length, not the area. So you just ignore the length, ignore the area. Consider that they are same. The only difference will come from the sigma. Sigma is 10 to the power 7 times bigger in copper compared to the dielectric. So if you can find out the resistance of the copper, you know what is the resistance of the dielectric. It's just 10 to the power 7 times lower. Isn't it? So whenever you try to find out the resistance of the copper, so you found out the resistance of the copper at the very beginning, right? So from there, you try to make a guess that what could be the resistance of the dielectric inside. You don't need to take care of each of these pi r square relation, because I know that you can do it. The idea here is not to make you a calculator, is to just make you a good human who can make a judgment out of it. Okay? So I know that it is not easy. I'm not saying that it is easy that from tomorrow you'll be a better, good, you'll be able to practice judgment. It's not like that, but it's a continuous practice. If you do this practice from now on, maybe 5 years later, you'll be much better. And please bear in mind that no one is trying to make you a calculator. We have much better calculator than you. So I do not know what other exam questions are, like what is their style. Every person, every instructor have different style. At least for my case, be sure that the answer that I will be giving you in the MCQ, they will be far apart from each other. Far apart. Like even if you can guess a ballpark, you're good. Okay, so try doing this. Instead of using calculator, can you just use your mental math to get to an answer, which is very close to the actual answer. And then try using calculator. Let's see if you can save your time. Okay? Thank you.